Hello my dear students, welcome back to the second lecture series of feedback amplifiers, which is the third module in analog electronic circuits. I'm Bhaskar, working as assistant professor in the Department of Electronics and Communication Engineering, SJBIT Institute of Technology. So before we move on to the articles of today's discussion or the learning objectives, we'll try to recall the things that we discussed in the last class, because recalling is always very important for us. Fine. So in the very beginning, what is basically a feedback? We took an analogy as well to understand it, and we got to know that feedback is something where you try to take the part of the output and feed it back to the input. Correct. And later on, we also understood what are the two different types of feedback. One is called the positive feedback, other one is called the negative feedback. And then we wrote the general structure of a feedback, and we tried to derive the expression for the closed loop gain, AF. We got it as A divided by 1 plus A beta. And later on, we also understood why do we have to use a negative feedback. Correct? What are the advantages of it? So we got to, know that there are many multifold advantages of a negative feedback, like the bandwidth increases, the gain gets stabilized, the input impedance increases, the output impedance reduces, and what else? The distortion is going to come down. It's basically a nonlinear distortion that we were talking about. And then what else? The noise is also going to come down. And we also had the mathematical feel of all these advantages. We mathematically got to know that yes, there are these advantages available as far as the negative feedback usage is concerned. Correct? So these were all the things that we discussed in the last class. Now we shall move on to today's discussion topics. Number one is topologies of feedback. We'll also be talking on the first two different types of topologies. One is shunt series and shunt feedback amplifiers. These are the learning objectives. Number one, what are the different feedback topologies that we have got? How do we identify the given topology as so and so, or the given feedback amplifier as so and so topology? We'll also get to know things on shunt series as well as the shunt feedback amplifiers. So before we get into the topologies, I think we must be in a position to get to know what are the basic types of amplifiers available. Anybody can name those? Probably we are very familiar with what is called as a voltage amplifier, and we always think that that is the only kind of amplifier available, but we are wrong. The first type is anyways a voltage amplifier, but other than this, we also have got something called as a current amplifier. Then trans resistance amplifier. Probably none of us would have heard about this. Trans resistance amplifier. And lastly, the trans conductance amplifier. Now let's look into the simple block diagram of it, like how this amplifier is going to look like. A voltage amplifier is very simple to realize, or very simple to imagine. We apply the input voltage and we expect an output voltage, correct? And the box which is connected between the input and output, we call it as an amplifier. We know how to represent the gain of it. What is it? It's basically AV, which is V0 divided by Vn, correct? It's V0 divided by Vn. So in voltage amplifier, both the input and output quantities are voltages. And what we get as a gain is basically a voltage gain. Hence it is called as a voltage amplifier. Okay. Now let's see the current amplifier. How does it look like? A current amplifier is looking like this. Very obvious that both the input and output quantities must be a current quantity. Why? Because finally the gain, when I find, it should have only the current values, I0 by II. So hence the name current amplifier to it. Then we have got something called as a trans resistance amplifier. So in trans resistance, how do we represent or write a resistance? Resistance is nothing but V by I, correct? So if I want to represent the gain of this block, which we are calling it as a trans resistance amplifier, we write it as V0 by II. So the input will be a current quantity and the output will be a voltage quantity. Hence it is called as a trans resistance amplifier. And lastly, we have got something called as a trans conductance, which is inverse of resistance. So at the input you will have a voltage quantity and at the output you will have a current quantity. And the gain is I0 divided by Vi. Remember, in the last two amplifiers, we are using the word trans because we are trying to relate the output voltage or current by input current or voltage respectively. In the third case, trans resistance amplifier, output voltage versus the input current, correct? output voltage versus input current. So two different quantities are taken which are totally different, voltage as well as the current. So hence the word trans comes in the picture here. So these are the basic four different types of amplifiers. Remember, when we try to arrive at the topologies, we are going to use these basic amplifiers and try to connect the amplifier, the feedback network. So based on that, we are going to say that it is so and so topology. Okay. So it is these four basic amplifiers which plays a major role, but beyond it, we have negative amplifier which gives us the advantage. So what we'll do now is we'll quickly try to understand as to how we arrive at the topologies. Okay. So what I'll do is I'll take a simple the structure that we used in the previous lecture series. We have something called as a source. Then this gets applied to the amplifier. Let's call it as A. And then we get an output. I will not indicate the load here because it is very obvious that a load will always be there because we have to use it for some application. And then we get this feedback network. So what will the feedback network consist of? It will consist of beta, correct? And then that goes back to the input side. So from the basic definition, what we say, a part of the output which is taken out from this point, or I can use the word sampled. A part of the output is sampled and fed back to the input side, and at the input side it gets what we call it as mixed up. So we can call this as mixer. So we have arrived at two different terminologies. Now one is called as a sampler, other one is called as a mixer. Let me call it as a sampler. Okay. So what a sampler will do, it will take a part of the output and feed it back to the input side. It is going to take a part of the output. Feedback network will feed it back to the input side, and mixer will mix it. In what way it is going to mix, or in what way the sampling is taken or done, it depends on what quantity we are interested in. Okay. So let me look at the four different amplifiers that we have. The four different amplifiers, let me write down: a voltage amplifier, a current amplifier. Let me write these as amplifiers. Then what do you have? Trans resistance amplifier and trans conductance amplifier. So let me make a tabular column indicating what are all present at the input and output of it. So let us say this is input, or let me start with an output because I first sample it and then mix it. First is output, second one is input. Why did I write like this? Because in feedback, first sampling comes in the picture and then gets mixed up. Without the sampled value, how can you mix anything? Correct. There cannot be anything in the feedback without sampling. So I'm writing the output first. Okay. And remember, when I give the names to topologies, the same rule is followed. The first word comes from the output side, the second word comes from the input side. Okay. So let us write the input and output quantities that are available here quickly. Oh, fine. You're good to go now. So can you recall from the previous slide as to, in case of voltage amplifier, what will be the output? I want a quick answer on this. Yeah, it is output voltage. And what will be the input? It will be a voltage again. Let me call it as Vn. Current amplifier. What will be the output? It will be a current quantity. And what will be the input? It will be a current quantity again. Trans resistance. It's very simple to remember. When I say resistance, you say V by I. And V is relevant to the output and I is relevant to the input in this case because it's an amplifier and we are defining the gain. So it will be V0 and In. Very simple to remember. Transconductance is reverse of resistance. So it is I0 divided by Vn. I0 divided by Vn. Let me erase this and write the correct one. I0 divided by Vn. Oh. So I hope till here things are all very clear to you. I think we are going in the right way. This is output and this is Vn. Now let us consider one kind of basic amplifier. Let us say it is a voltage amplifier. Let's say Now looking at this tabular column, one can obviously say what is the quantity that I am sampling at the output. It will be a voltage value. I want to ask you a very simple question. If I want to take a part of the output, what will I normally do? I will take it always across, correct? Supposingly, if I have an output terminal, let us say this is a output terminal. We are considering a two-port network. Here in the block diagram, even though we have written a single port, but normally all amplifiers are two-port networks. So I'll consider a two-port here. Two lines indicates two-port network. Okay. So this is where the output of the amplifier is coming. I want to take a part of the output. What will I do? Can I connect it in series? I can never do that. Voltages are always taken across, correct? So I'll be trying to take it across this and feed it back to the input side like this. This goes to the feedback network. So what I'm trying to convince you people here is, when I want to sample an output, I'll always be taking it across. When I want to sample an output, I'll always be taking it across. When I want to sample a current, I'll take it in series. So let me write that. All very basic things which all of us know, but I'm trying to just put it in the right way here, that's all. So when I want to sample, let me write it as sample here. When I want to sample a voltage, I'll take it in shunt or parallel. Let me write it as shunt. When I want to sample a current, what will I do? I'll connect it in series. Now I want to mix up at the input side. Now the voltage is being sampled and the feedback network will take it towards the input side. Now what should I do at the input side? Remember, we are talking about a voltage amplifier, and the quantity that has to get into the amplifier is again a voltage. So while mixing it, I should mix with the source signal. And when mixing happens, as far as the voltage is concerned, remember, I cannot connect it in parallel. It will be nonsense if I connect it in parallel, because two voltage sources connected in parallel will give you what we know, correct? So what will I do? What is it I'm going to do? I'll connect it in. Any good answer? In series. So I'll say, as far as mixing is concerned, let me write mixing here. Mixing voltage value will be what? Series. When it comes to current, I'll have to connect it in shunt. If you remember, or if you understand these two rules that I've written here for sampling as well as mixing, then we are good to go with the topologies. We can understand, or we can now list out the topologies that we have got as far as the feedback amplifier is concerned. Okay, are we good to go? Can we move ahead now, or do you really want me to write how actually the block diagram will look like? We shall see it, don't worry. Once you are through with all these things, if you can recall and if you can remember and understand these points what I've told, then it is very easy for us to write the topologies and even understand it as well. Okay, now I think it's good time for us to list out the topology. And the four topologies are shunt series, series and shunt, series, shunt and shunt. If you please recall the point that I told, the first word in the topology name or terminology indicates the sampling part, and the second word indicates the mixing part. So depending on whether you have a voltage or a current, for a sampling, if you want to sample a voltage, how will you do it? You will shunt. If you want to mix the voltage, you will do it in series. Likewise, if you want to sample a current value, you will connect it in series. And if you want to mix the current value, you will connect it in shunt. So please do not forget this. Okay, please do not forget this. So keeping that in mind, what is happening in a shunt series is, remember the basic amplifier, what is being used is a voltage amplifier. So the first terminology is in all these four categories indicates the basic amplifier. It indicates the basic amplifier. And remember, finally we can call it as still a voltage amplifier, but now it will contain the feedback part. And what kind of feedback? It will be this kind of feedback, depending upon what kind of basic amplifier we have got. So as far as the voltage amplifier is concerned, we will have what kind of feedback? It is called as a shunt series feedback. Why is it called as a shunt series? Because voltage is being sampled and voltage is again being mixed up at the input side. Coming to the next kind, current amplifier. What kind of feedback is being used? It is called as a series shunt. Why is it called series shunt? Because the current sampling is happening and the current mixing is happening. Why do I say current sampling and current mixing? Because in case of current amplifier, both the input and output parameters or quantities are current values. So when you want to sample the current, how will you do it? You will take it, you will tap it, correct? You will have it in series. And when you want to give it back to the input side as a feedback, remember it's a negative feedback. So you should bear this in your mind. So if you want to have a negative feedback concept being applied there, as far as the current value is concerned, you have to shunt it. In the sense, you have to take it out of the source. So IF would come out of the source, and later on it will continue as IN. So IF part is getting eliminated from IS, and that is why it is shunt. Third kind of amplifier is basically a transconductance amplifier, which is also called as a series feedback. Why is it called as a series? Transconductance will have what quantities as input and output? It is conductance. Sampling, what are we sampling? We are sampling the current value, so hence it is series. And we have to mix the value. What value are we mixing? We are mixing the voltage value, and again it is series. Hence the word series comes into picture. And lastly, we have got what is called as a trans resistance amplifier. What are the quantities that we see here in trans resistance? It's the resistance value. So it is V0 and IN, correct? So we call it a shunt. Why is it called shunt? Voltage is getting sampled because at the output we have got voltage. So it's getting sampled. So it should be a shunt. And the current is getting mixed. So when the current gets mixed up, it is again a shunt. So this is how the four topologies will get its existence in the basic amplifier. So depending on what kind of basic amplifier we have got, we are going to choose or have so and so kind of feedback network. And the names are given in this way. I hope you are okay with this. So the next slide what we have here is going to give you a much more elaborate or much more better understanding of the four different types. Now we shall try to name these because I have not indicated the name purposefully. Looking at these blocks, we shall try to name those. Okay. So let me use a different ink for that. So probably a blue one will do for me. So first we have A, which is a basic voltage amplifier. So in a voltage amplifier, what you will have? You will have the output voltage and you will have the input voltage. Vn and V0 available. So right here, we will have what is called a Vin. Vin plus and minus. We'll have even the output voltage right here. This is where the output voltage is coming. And we'll always take it across. If you can see these 2 points, we are taking it across. Correct? So that is why the word shunt comes into picture. So I can say shunt right here. Now how are we feeding it back? Remember, we have a voltage quantity here. So I should be using the voltage value here as well. So everything should be in terms of voltage here. So when I am feeding it back, I'll be feeding the voltage value. And how will I feed the voltage value? It will be in series. So the word series comes into picture. And when I'm writing the terminology or giving a name for this kind of amplifier, I'll take up the sampling part first and then the mixing part. So what is the name that we give for it? It is called as a shunt series amplifier or shunt series feedback. Or what kind of feedback amplifier it is? It is also called a voltage series feedback amplifier. Why is it called as a voltage series? Because shunt is nothing but it is relevant to voltage value and series is retained. So these are all the different ways of giving names for the same amplifier of the block diagram. So different authors would use different terminologies and we should be aware of all these things. Okay, there is nothing to really get confused here. if you are thorough with the concept, if you know what is the basic amplifier doing, what are all the quantities that it has got at the input and output side, it is very easy for us to really identify the feedback topology. Okay, so let's come to the next one, which is B. What is a basic amplifier being used? It is a current amplifier. What do we have at the input side? It is IN. What do we have at the output side? It's basically I naught. So I want to sample the output current, and when it comes to sampling the output, we do it in series, correct? We do it in series. Now I want to feed it back. Remember, at the input side of the amplifier, I've got the current quantity. So everything should get converted to the current value or the current quantity. So Vs will now become Is. So we have converted a voltage source into a current source, and you know how to do the conversion. So current source comes in parallel with the resistance offered by the source. So that becomes the source part. Now the feedback comes into picture, and feedback should also be the current value, correct? If I want to mix the current, you know what to do. I should tap it so that when Is gets in here, a part of Is should get lost. So it means when In is written, I'll be writing it as Is minus of In, which indicates it's a negative feedback. Got the point? And how is the current feedback shown here? It is in shunt. So can you name this now? Club these two together, that's all. First comes the sampler part, next comes the mixer part. So I'll be calling it as what kind of amplifier? It is called, yes, series shunt amplifier. And what is the other name that we can give for it? Series is as good as what? Current, correct? You can also call it as a current shunt feedback amplifier. But remember, the basic amplifier will still be the current amplifier. We can still call it as a current amplifier, but with this kind of feedback. Clear? How about the third one? C. The basic amplifier is basically transconductance. Transconductance means it has got current at the output and voltage at the input. Now, how will you sample the current value? It is in series, so I should use the word series. You can see things are all connected in series, correct? Things are all connected in series, and it goes back. Input at the amplifier is a voltage, so everything should be in terms of voltage. So we have a voltage source back, and we should feed the voltage back to the input, but it should be a negative value. So I feed it in series. So this is basically a series. So we can call this as what? Series. This is also called a current series amplifier. Or we can as well retain the name as transconductance amplifier, but with this kind of feedback, series feedback. Okay. Lastly, we have got this. What is it? A trans resistance amplifier. What do we have at the output? We have a voltage value. What do we have at the input? Remember, it is a resistance. So output voltage versus the input current. Its output voltage by input current is what is trans resistance amplifier gain equation. Okay. So if I want to sample the output, you know what I have to do? It's in shunt. If I want to feed it back to the input, again, as the current value is there, remember, you can see the source has now been converted to a current source. So you should have a shunt tapping. So both are shunt. So we can call this as what? Shunt feedback. Or shunt is as good as what? A voltage. Or it is also called voltage shunt. Okay. This is the topology, understanding of the topology, and this is how we really identify the topology. I hope this has made you very clear as far as understanding the topologies are concerned. This is one more way of writing the same thing. I have not done much changes in this, but instead I have brought in these four things, that's all, to indicate what they are. These dependent voltage or current sources have been brought here to indicate a much more better understanding or much more insight into the different topologies that we have got. Probably I can explain one and tell you what is the meaning of it. Now this is what kind of amplifier? This is a voltage amplifier. This is a voltage amplifier. And how would you define beta in case of voltage? amplifier, it will have VF at the feedback part, and at the input of the feedback you will have V naught. Correct. This is as good as writing it as VF equal to beta times of V naught. And what is this? This is nothing but VF. And we are writing that VF as beta times of V naught. So we are just indicating a dependent voltage source there. So likewise, you can do it for all the other three and understand what those current or voltage sources indicating there. They are basically indicating the feedback quantity, okay, which is nothing but the amount of voltage or current that is getting in back to the input side in the out of phase way. Okay, so this is all about the topologies. Okay, now we shall see few characteristic parameters of the first kind of amplifier, which is a voltage amplifier with negative feedback. Remember, in the objectives we had said that we are going to talk about two different types of feedback topologies. Correct? I've taken it as a voltage amplifier with a negative feedback. So what is the name that we are going to give for this? It's basically called a shunt series feedback, or it is in simple words called as voltage series feedback amplifier. Feedback amplifier. Okay. Now we are going to talk about this voltage series feedback amplifier. And what and all are we going to talk about in this? In this voltage series feedback amplifier, we will be deriving the expression for the gain. We will also derive the expression for the input impedance. Let me call it as ZIF. We will also be finding out the output impedance, which I'll call it as ZOF. And let's see whether the gain reduces, the input impedance increases, and the output impedance reduces or not. Okay, we shall look at these parameters. And we can even derive the expression for the bandwidth and all other things. But right now we are not interested in that part, but we'll only worry about these three parameters just to get a confirmation that the amplifiers, what kind of amplifier will give what kind of characteristic nature, or will show up the characteristic nature. Okay, so let's do it one by one. Before we do it, now we should be writing the block diagram for it. So I shall use the same block diagram which was shown earlier. So there is an amplifier. We have got the feedback block. Now at the input side you will see a source. We will call it as Vs. Let me also indicate the polarity for it. We'll indicate Vin at the input side. Let us also have the polarity for it. Let me take out the signal from here. Let's call it as minus. Now at the output, what we will have is again a voltage value. So I shall indicate a load resistance right here. I shall write it as RL. What are we getting here? We are getting V0 value here. Now the feedback has to go. The sampling will begin now. So when you are doing the sampling, you will take it this way and put it right here. And this point will be taken and fed back to the input side. Now the voltage, part of the voltage is getting back. Now at this point, you will see the voltage getting fed back to the input side. Like this. Now what do you observe? You will see the voltage Vf getting fed back to the input side. Okay. So look at the polarities that I have written here. Now we should have a confirmation that this feedback is really providing a negative feedback or not. For that, what we'll do, we just try to apply KVL to this loop and try to see what kind of what is the equation that I get for Vin. Remember, we should get Vin as what? It should be Vs minus of Vf. This is when you say that there is a negative feedback effect, because the actual input which is getting into the amplifier should get reduced. Correct. So it should be lesser than the source voltage. That is when you say that there is a feedback effect. So when you apply KVL to it, what will you get? You will get Vs minus Vn minus Vf equal to 0, which would imply Vn is equal to Vs minus Vf. And what you have got here and what is required are one and the same. So hence this is basically a negative feedback. Okay. Now let us try to derive an expression for the gain. Okay, we'll derive the expression for the gain. So what I'll do for it, we will use the same block diagram and we will try to derive it. What is the equation for the gain? A is what? A is equal to V naught divided by Vn. Can I also write it as V naught divided by Vs? Is it possible? Are these two quantities the same? If you look at this block diagram and say the answer is not correct, because Vs is different and Vn is different, because Vs is what? Vn plus Vf. Correct. Vn plus Vf is what is Vs. So V naught by Vn is not same as V naught by Vs. But this is true only when Vf has become equal to 0. So initially there won't be any feedback at all. Why is that so? Because initially when you turn on the amplifier, there may not be any output. At that instant of time, there may not be any output. So assuming that condition here, I can write A as V naught by Vn, which is equal to V naught by Vs. Now we shall see what is Vn equal to. Vn, we know it is Vs minus of Vf. So what I'm going to do further is all kind of playing around with these equations and finally arriving at an expression for AF, which is V naught divided by Vs. My point is that. Okay. So what I can write further? I can further write equation for V naught. We know that V naught is equal to what? V naught is equal to A times of Vn, because we have that equation right here. Fine. So I can write it as A times of Vn. Further, I can write it as A times of what is Vn? I'll bring this equation here. So I shall write it as Vs minus of Vf. Or I can write this as A times of Vs minus A times of Vf. Now I should worry about the Vf. What is Vf? Vf is nothing but beta times of V naught. And how did I get this equation? I got this equation from beta, which is nothing but V naught divided by, Vf divided by V naught. Okay. So I shall put that Vf here. So this would now imply V naught is equal to A times of Vs minus A times of what is Vf? It's nothing but beta times of V naught. Slowly, if you observe the steps that I'm writing, we are trying to have only the terms which contains, or in the equation I should have only the terms like A, beta and AF, or things relevant to AF, which is V naught and Vs. Slowly I'm trying to eliminate the terms which are not required for me. If Vf got eliminated now, correct. Vf is anyways retained, V naught is anyways there, and I've got this A and beta coming into picture here. So what I can write, I can take this to the left hand side and say V naught into 1 plus A beta is equal to A times of Vs. Now it is very clear that AF, which is defined as V naught by Vs, go back to your first lecture series that we had discussed about the basics of the feedback, where we defined what is the closed loop gain AF. It is nothing but this is equal to A divided by 1 plus A beta. So it means we are able to get the same gain equation what we had defined there. So all the negative feedback amplifiers, irrespective of what topology are we talking about, all the negative feedback amplifiers will have this kind of AF equation. A might differ because depending on what is the basic amplifier, A would be V naught by Vn, or it could be V naught by In, or it could be I naught by Vn, or it could be I naught by In. Depending on the basic amplifier, A equation would differ, but otherwise A divided by 1 plus A beta, the standard representation of AF equation will remain as it is. Okay, so the first part is over. So we could able to find the gain. Now we shall move on to the next thing. What is it? It is input impedance. Input impedance. How shall I find the input impedance now? So to find the input impedance, I'll have to tweak the block diagram that we had written. That is, this block diagram needs to be slightly tweaked so that I bring in the other parameters relevant to the amplifier. So I think you've studied about the small signal model of an amplifier in the first module for BJTs and FETs as well in the coming modules. So you know how to basically write or represent the small signal model of a amplifier or a transistor. So I shall use that concept here in deriving the expression for the input impedance. Okay, so how will I write it? Let me use a different ink for it. Let me use a black one. So the block diagram is written like this. So you will have a resistance of the input, and what do you normally call this resistance as? If you are using a RE model, we would normally call it as a beta RE, correct? Which is the input resistance of the transistor in CE configuration. But otherwise, I'll write it as RI. I'll write it as RI. And what do you have at the output? You will have a dependent source. What kind of dependent source are you going to have now? You will have a dependent voltage source. Why did I use the word dependent voltage source? Because the input what you are feeding now is basically Vin right here, and that is why you will have a dependent voltage source. So let me write the dependent voltage source this way, even though the notation may differ, but I'm more interested in this A times of Vin. So this entire thing what I've written here is indicating your amplifier part. Okay, is this point clear to all of you? So this is a small change what I'm going to bring in. Otherwise, rest all will remain the same. You don't have to worry about any other thing. Rest everything is going to remain as it is. You don't have to really bother at all. So you write the rest of the things in the same way as I wrote for the previous one. Even the beta factor will remain the same. I shall take the output from here and feed it back to the input side. And at the input you will have a voltage source, plus minus Vs, this is plus minus Vn. Let me take this and connect it to the feedback path. That's it. Okay, so except the small change which I've written within the dotted box, everything else is retained as it is. Absolutely no change in it at all. And probably I can include one more thing here just to have the completeness, a resistance, which is indicated as R0. So this is as good as your small signal model that you've written for a simple transistor, CE, CC or CB configuration, anything. Or it could even be relevant to the the FETs. In FETs you don't see this RA because it's always open circuited. But otherwise you can see a RG which is externally connected. But right now these are all internal parameters of the amplifier. Okay. So what is going to be RIF in this case? RIF is the resistance that you look in from this point. Standing at this point, that is before the feedback, in the sense standing at nearing to the source and looking into the network, looking into the input terminals of the amplifier is what is RIF. So that is what is we are interested in now. So to find out this RIF, what is that I have to do? So let's begin with it. Let me write the current here as some IN. Remember, the current will remain the same. Current will not change because everything is in series. So the current is going to remain the same. IN remains same everywhere. Whether you indicate it here, here or here, it remains the same. So what is the equation for IN that I can write? IN is equal to, good guesswork. IN is equal to Vn divided by Vn divided by Rn. I've written it as Ri, so let me retain it as Ri. So when you are standing here at this point and when you look at the circuit or look into the circuit, what you see is only Ri. Correct? But when you stand here at this point and look into the network, it wouldn't remain as Ri, but it will be RIF because the feedback also comes into picture there. Getting my point, all of you? So This IN that I've written here is right now considering this voltage and the resistance that is offered by the amplifier alone, which is Ri. Now this can be further written as what? I can write it as Vs minus Vf divided by Ri, because I know what is Vn equal to. Then I can write this as Vs minus beta times of V0 divided by Ri. And lastly, I can say that In, this would only imply that In is equal to Vs minus beta times of what is V0? There's nothing but A times of Vn divided by Ri. Okay. Now I should make some, alterations or changes in this. I'm slightly tweaking this equation that I've got here. I'll write In into Ri is equal to Vs minus A beta times of Vn. I just brought this Ri to the other side. Later on, I can finally say Vs is equal to In into Ri plus A beta times of Vn. Now what is Vn? You can see here this equation says what is Vn. So I'll write this as In into Ri plus A beta times of In into Ri. I've got In into Ri common, I can take it outside. In into Ri times of 1 plus A beta. So further what I can do, I can write this equation as Vs divided by In, which is equal to Ri times of 1 plus A beta. So you get Vs by In. Now the question is, what is Vs by In? Remember, Vn by In we called it as Ri. This equation says Ri is nothing but Vn divided by In. So that is standing at this point. You're looking into the network standing at this point. But if I stand slightly behind and see, which also includes the feedback, what will be the resistance offered by the network or the impedance offered by the network? It will be Vs divided by In, because the source voltage now comes into picture. So including the source, if you try to see what is the resistance offered, what you will observe is this equation. So what is written here is basically Rif, which is equal to Ri into 1 plus A beta. Or in general, you can say the impedance offered by the voltage amplifier, the input impedance offered by the voltage amplifier with feedback is Zif, which is equal to Zi times of 1 plus A beta. Okay, so just to maintain the simplicity, we took this Ri and Rif, but later on we can as well convert that to a impedance value. And the equations will all remain the same except that the notation has got changed. I hope this point is very clear to all of you. So what do we conclude from this equation? We conclude that the input impedance has increased. By what amount? An amount of 1 plus A beta. Go back and check the equation that we had written earlier in the first lecture series, where we said that the input impedance is going to get increased by an amount of 1 plus A beta, and the same thing is happening even here also. Is this point clear to all of you? Yes, I hope so. Now what I'll do, I'll try to represent. We are interested in finding out the output impedance now. So let us say output impedance. Even though I'm using the word impedance, but we are using resistances everywhere. But later on we can generalize it to impedances. Okay, R becomes Z, that's all. So in the process of finding out output impedance, what are we doing? We'll have to follow a procedure. The procedure is like this. If at all you are interested in finding out the impedance or the resistance of the output of a circuit, you will always nullify the input. Correct? If there is a voltage source, you will make it 0. Correct? If there is a current source, you will open circuit it. Correct? So there is a voltage source here. I'm going to nullify it. I'll set this value to 0. So it means it's as good as shorted. It is as good as shorted. and I'll include a voltage source at the output, and I'm calling it as V, and the current which is derived because of this voltage source is basically equal to I. Now what I'll do, I'll apply KVL to this loop. I'll apply KVL to this loop. What will I get? Applying KVL to the loop, consisting of V R naught and A B in. What will I get? You will get this as, when you apply KVL, I'll straight away write the equation. V is equal to I times of R naught plus A times of V in. In the actual sense, you will get V minus, you will have it as V minus I into I naught, R naught minus A times of V in is equal to 0, and finally this is the equation what you get. So I'll have to make some changes in this. So what can I write? Let me try to remove this V in. Somehow I need to eliminate that V in. So what will I do? I'll use the equation for V in. What is V in equal to? It is Vs minus of Vf. But we have used a small procedure here. What is that? Vs has been set to 0. So I'll make this equal to 0. So you will have Vn equal to minus of Vf. So I can write this equation now as, the further implication is I into R naught minus A times of Vf. But Vf is what? Vf is what? Vf is nothing but, let me write, V is equal to I times of R naught minus A times of, what is Vf now? In the normal circumstances, we are writing Vf as what? Beta times of V naught, where V naught is the output. But right now, V naught is getting replaced by V. So this equation will be beta times of V. So I can write Vf as beta times of V. So when you rearrange all these terms, what you will get? V into 1 plus A beta is equal to I into R naught. Remember, my interest is to find what is ROF. And if R naught is available here, ROF will be available after the feedback. So this is ROF. If you are standing at this point and look into the network, you'll be able to see what is the resistance of the impedance offered by the amplifier considering the feedback, because that is a point where the sampling is happening. So you stand after the sampling point, and when you look back into the network, you see the resistance or the impedance reflecting that, and that is what is the output impedance. And how would you define this ROF? You can define it as V divided by I. So your job is to arrive at this V by I. So from this equation, it becomes so very clear to us that V by I is equal to R naught divided by 1 plus A beta, which is equal to ROF. So this is the output impedance offered by a voltage series feedback amplifier, or it is a shunt series feedback. So in simple words, we can call it as a voltage amplifier with a negative feedback. And what is the conclusion you draw from this? The conclusion what we are able to draw is the output impedance, the output impedance is reduced by an amount of how much? 1 plus A beta. And is a conclusion what you draw. Okay. So the summary what we can put is gain, and we can also write ZOF as what? Z0 divided by 1 plus A beta here. Okay. Let's now summarize the voltage series. Summary of voltage series feedback amplifier. The summary is like this. We'll have the gain, we'll have the input impedance, we'll also have the output impedance. What is the gain equation? Gain equation is A divided by 1 plus A beta. When I say gain, I am concentrating on AF value. What is ZIF? ZIF is ZI times of 1 plus A beta. And what is ZOF? It is Z0 divided by 1 plus A beta. This is the summary that we can have for a voltage series, or also called as a shunt series feedback amplifier. Okay, let's move on to the next kind of amplifier, and the next one is voltage shunt amplifier, or it is called as a shunt feedback amplifier. Okay, this is the block diagram which we have already seen. At the input side, you have got a current source, and you have to notice it. Okay, because it's a voltage shunt. At the input side, as far as mixing is concerned, you are mixing the current value. So the source should be a current value. Okay, so now we shall try to find what is the impedance of it. Remember, I don't have to really again find the gain of it, because as I already stated in the previous discussion that we had on the voltage series, that all the amplifiers will have the gain as A divided by 1 plus A beta. So it holds good even for this also. You can give this a try. Okay, you just have to follow the same procedure what we followed for the previous one. You'll be able to find what is the gain of it. Okay. Now coming to the input impedance, what is the input impedance offered by it? So let us see what is ZIF. Okay, so let me find, say, input impedance. How will I find the input impedance of it? So it is indicated as RIF. So input impedance RIF is defined as what? RIF is nothing but Vn divided by Is. You must be wondering, where is that Vn? Vn is nothing but the voltage which drops at the input terminal. Okay, we shall see that. Finally, my idea is to find an equation for this, Vn divided by Is, which gives me what is RIF equal to. So I'll use the same equation or the same definition of RIF in finding out or deriving the expression. So I'll say RIF is equal to Vn divided by Is, which is equal to Vn divided by, now what is Is that I can write? I can apply the current formula here, in the sense the KCL. Is is nothing but If plus In. So Is is nothing but If plus In. So I'll write this as If plus In. Further, what I can do, I can write the expression for If as what? I can write If as, let me write that here, Vn divided by, If is nothing but beta times of V0. So I'll write beta times of V0 plus In. I can still further make the changes here. What is it? I can divide both the numerator and denominator by In. Let's do it. So when I divide both numerator and denominator by In, I'll get it as Vn divided by In whole divided by 1 plus beta V0 divided by In. This is what I get. So what is Vn by In? Vn by In, let me write, Vn divided by In is nothing but Rn. It's nothing but Rn or Ri. It is this value. Okay. So I can write this as Ri divided by 1 plus, what is V0 by In? V0 by In is what? It's nothing but the gain of the amplifier, because what kind of amplifier is this? If you go back and check, it's a voltage shunt amplifier. So output has got the voltage value, input has got the current value, so it's V0 by In. That becomes the gain equation for it, and that is nothing but A value. So I can write this equation as 1 plus A beta. So RIF, sorry, this should be RIF is equal to Ri divided by 1 plus A beta. What is the conclusion you draw? The input impedance is the input impedance with feedback. Let me conclude it. The input impedance with feedback is lesser compared to without feedback. without feedback. Okay, this is the conclusion what we draw. Is this clear to all of you? Yes. Let's look at the output impedance calculation now. I already have the circuit with me. This is for output impedance. Output impedance. So when it comes to the output impedance calculation, what are we doing? We'll follow the same procedure what we followed in the previous topology, where we made the input voltage to set to 0 value. Correct? Here I'm going to open circuit it. Anyways, I'm going to make the value of Is equal to 0. So I'll say Is is made equal to 0, and we'll connect a known voltage source at the output, which is equal to V, which provides an amount of current I to the circuit at the output. So what do we do next? We will try to derive the expression for what is called as ZIF. How do I define ZIF? Sorry, it is ZOF now. We are finding out the output impedance with feedback. So it is ZOF, which is equal to what? Which is equal to V divided by I. Fine. So my idea is to find an equation to this V by I. So we'll go ahead with it now. So what do we do? As I've already told, Is is set to 0 and we have connected a known voltage source V. We can apply KVL to this loop and find the expression. So let's do it. So when I apply KVL, what will I get? I'll get V is equal to AI or AN. We have written it as AN plus I times of R naught. Correct? This is what I get. Further, I can also write this as V is equal to A times of. Now when I am writing this IN, as already Is is set to 0, let's write the equation here. What is Is minus If equal to? Is equal to IN. We have already set the value of Is equal to 0. So what is going to happen to IN? It becomes minus If. So IN is basically equal to minus If. So I shall use that minus If plus I times of R naught. So you can write this as minus AIF plus I times of R naught. Okay, this is what you get. What next? But what is IF equal to? IF is nothing but beta times of V naught. Correct? Because beta is what? IF divided by V naught. So I can write IF as beta times of V naught. So I can now say this V is equal to minus A times of beta V naught plus I times of R naught. Okay, so I can write this as, and what is V naught? What is V naught? V naught is nothing but V. So I can write this as beta V. So let me write here straight away as beta times of V. Beta times of V plus I into R naught. So what have we got? This would imply further V plus A beta times of V is equal to I times of R naught, or V divided by I is nothing but R naught divided by 1 plus A beta. Okay, so this is the equation for ROF that you get. So ROF is nothing but R naught divided by 1 plus A beta. And what is the conclusion you draw? The output resistance or output impedance, I can as well write this as ZOF, which becomes Z naught divided by 1 plus A beta. The conclusion what we can draw from this is that the output impedance is lesser in amplifiers with feedback, because it's very clear that ZOF is lesser than Z naught. Okay, so we can summarize the voltage shunt. So what is the summary? The summary what we can quote here is, as far as the gain is concerned, which is AF, as far as the input impedance is concerned, which is ZIF, and the output impedance is concerned, which is ZOF, we can say gain is AF divided by A divided by, it is A divided by 1 plus A beta. And what is happening to ZIF? It is nothing but ZI divided by 1 plus A beta, and ZOF is Z0 divided by 1 plus A beta. So there is a point that we have to know. Gain is anyways fine, but the input impedance has come down here, and so is the case with the output impedance also. If you try to compare this result with the previous topology that we had discussed, which is voltage series, input impedance raised and the output impedance came down, which was kind of a required characteristic for a good amplifier, but in this case it is the other way around. Okay, so with this I conclude the second topology, which is the voltage shunt feedback amplifiers. Thank you.